Hey everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. And I like to bring you behind the scenes, talking to the people who are making the news, the researchers, the scientists. And so today, we're going to be talking about photonics and space power. So welcome to the show. So,
Hi, nice
so,
to
so
be here.
the question I always ask people, who are you? What do you do?
Okay, well, I'm Stephen Sweeney. I'm a physicist, and I'm a work at the University of Surrey in the UK, and I'm a physicist that specialises in something called photonics. And photonics is all about the science of light, right? Or how we use light and how we can do interesting things with it. So really, everything that I do in some way involves using light and trying to do something that we can all make use of. In fact, for example, today, just talking to you on this in this remote connection, we're using lasers that are firing signals through optical fibers, and those are kind of some of the things that we do.
Well, I'm using Starlink, so it's even going to space, which
There
is
you go, even
yeah.
more.
So does does photonics does it sort of narrow down the wavelength of the electromagnetic spectrum? Is it a certain part of it, or does it sort of include anything from radio to gamma rays?
Yeah, so we tend to focus more in the sort of visible near infrared region is where a lot of it happens. But of course, we can go beyond that. So there's an increasing amount of photonics happening in the mid infrared, and then even pushing out towards the terahertz, as it's called, because there are just loads of applications that we can use electromagnetic radiation in that range. So pretty much I guess we've probably expanded the boundaries of what we call photonics in the past few years.
But like, what is the like? Is photonics a fancy word for lasers?
Um,
Like,
Lasers are a big part of photonics, right?
right?
And a laser is a particular type of photonic device or instrument. Um, but really, no, photonics. I think years ago we used to talk about optoelectronics more, which was kind of like the how light and the electronics kind of come together. And it's become more about photonics now because I think it's also to do with how we directly manipulate light. So it's a very broad field. So photonics literally will do anything from, like I say, communications. It can be used in biology and medicine. It really can be used everywhere. So lasers are probably one of the most successful technologies that have enabled that.
I love just sort of like the story of lasers, how back when they were originally developing it, they really had no idea what it would be used for. And yet now lasers are every single part of our life. If
Mm.
something interesting is happening, you can probably find a laser in there somewhere,
Absolutely.
contributing.
I mean, I think it was called a solution looking for a problem, right? So originally,
Yeah.
and of course now that solution has found lots of problems. And I say to people, you maybe don't realize it, but there are probably several lasers in your house doing something. Back in the old days when we used to have compact discs and DVDs, of course, they were all powered by lasers. But now even like how we stream data over optical fibers to the home is using lasers for that, and the other technologies that we won't even think about, but that there's a laser in there doing some work for us.
Yeah, yeah. Now you came across my radar, which I don't know if that's part of photonics. Anyway, about a couple of months ago, I think, and you were working on some research to look into space power. And the viewers on this channel know I've been fairly, I don't know, dismissive. People are wondering when we're going to have giant space satellites beaming power down to Earth to power all of our hopes and dreams. And it's I think we're a long way off from that case, but you're working on a fairly interesting version of space power that really caught my attention. So, can you give us an idea of the research that you're working on for space
Sure.
power?
Yeah, sure. As I said, this is sort of a part of what we do. And I guess the nice thing about this research is it links a couple of areas of photonics together very nicely. Um, so, so we've spent many years working on developing lasers and different types of lasers for various applications, and also photovoltaics, which is the sort of the opposite, really. It's something that receives light and turns it back into electricity. And so the idea of this project really is it's all to do with, well, okay, we're very familiar with how we wirelessly transmit data and information, but actually we can equally do that with energy. And of course, most of the energy that we have terrestrially is brought to us through cables in some way, directly through wires. But we can do that wirelessly as well. And actually using electromagnetic radiation, so light, is a good way of trying to do that. So this project, really, I guess we started working on what we now call wireless power quite a few years ago. And actually some of the early stage work really was to do with some of the really big picture ideas like space-based solar power.
Yeah.
And that has now sort of evolved into many other applications, some of which terrestrial, and I'm happy to talk about those a bit later. But this particular project, we essentially teamed up with a company called Space Power in the UK, who had this really interesting idea of actually trying to solve a problem with satellites, in low Earth orbit in terms of their supply of energy. And so the basic idea of this project is essentially that is to take some of the ideas of how we can transmit energy using lasers and using that as a means of providing power to satellites in low Earth orbit. And the reason we need that, or why there is a need for that, is that really, well, number one, there are lots of satellites in low Earth orbit, and this is increasing significantly. I think there was estimated something like 8,000 active satellites in LEO.
Yeah, I think like 3,000 of them were supplied in the last couple of years, thanks to
absolutely. And the interesting thing about that, of course, is that it's going to get more and more, right? I mean, it's going to get more congested, more satellites, more launches, and so on, which is very positive in terms of the use of space for productive things. But I guess the things there is that we have to think about is, well, how do we provide energy to them? Because they spend quite a lot of their time. They go around the Earth maybe 11 times a day or something. They spend a good fraction of that time in the eclipse, so in the Earth's shadow. And of course, the solar panels on board those satellites effectively can't do anything when they're in shade. So they're essentially not able to really do very much. So there's a solution to that is, well, put big batteries on board those satellites, but of course that increases launch mass and so on, and also just more materials and so on. And so the idea of this was to say, well, actually, what if we could actually just get the energy to those satellites using other means? So in this case, using a laser. And that's the general idea. So we worked with Space Power on looking at this from a feasibility perspective. So we've done a lot of lab-based trials where we've essentially looked at, well, what are the conditions you need to satisfy in order to get sort of energy into those small satellites. And so a lot of the focus has therefore been on, what are the optimum wavelengths for the lasers? How does it depend on other factors that the satellite might experience? So, for example, temperatures. They can be operating in quite extreme temperatures. In the eclipse, they can be quite cold, for example. So we've been looking a lot at how we can develop a system that accommodates that. So there's a lot to do on both ends of that thing. You've got the laser at one end, you've got the photovoltaics on the satellites at the other end. So there's a lot of interesting photonics involved.
Well, when I envision a satellite in low Earth orbit, I'm envisioning a fairly small, satellite package, and then usually some giant winged, solar panel wings that are extending out from it. And then, as you say, in addition to these sort of fairly extensive solar panel arrays, you've also got a significant battery to keep it alive and warm through the eclipse portion of its journey. If you could beam it power, then you would need, and this is a thing I want to understand, less of a solar voltaic system, because it's essentially you're firing a very directed beam right at its solar panel, and essentially no battery system. So you're reducing and then all the electronics that goes along with that. Like, it sounds like you're just simplifying it down to whatever is the communication science package on the device itself. Is that?
Yeah. So I guess, I think that's you can consider that to be sort of one particular sort of case where you can go all the way to that extreme. But there are also intermediates, right? Where it means you maybe just don't have to have a very bigger battery on board the satellite, or you don't have to have quite as big solar panels. And of course, they're all useful in terms of satellite launches, in terms of the amount of mass that you have to launch, but also the materials cost. And the other thing, of course, to think about is just lifetime, because one of the other things about these is that they their sort of utilization rate of satellites in terms of how long they're up there is relatively low, right? And that's largely because of energy. And so I think there's some problems you can solve with this approach in terms of both launching satellites, but also just in terms of materials use, right? In terms of how much material you need to be able to fulfill the need, and maybe you don't need to launch quite as many satellites if they can last longer and do their job longer when they're in orbit. So I think there are different benefits. But what you say there is correct. At one extreme you might imagine that really you need a very minimal battery to actually achieve the operation. I think in practice you would, like I say, you'd still have a battery there. It's just that it wouldn't be anything like what you would need if you didn't have this additional source.
So what kind of range are you considering to be able to fire this laser? I'd love to know about the sort of the laser. How powerful is the laser? How far can it go? And then how big of a receiving photovoltaic system do you need to be able to power the satellite?
Yeah, so they're really good questions. I mean, so you're talking thousands of kilometers, right? So you're talking thousands or even more kilometers. Now, of course, lasers are the only really way you can do that. So a coherent light source that you can send in a collimated beam very controllably, and you can direct it very controllably. So really it's only the laser that really allows you to do this. And so the sort of powers, actually, that's an interesting question as well, because a lot of these small satellites don't actually use huge amounts of power. They can literally be down at the sort of hundreds of watt level, even less than a couple of hundred watts.
I mean, we were talking about this last night. The Voyagers are down to 4 watts.
Yeah.
And still sending data back to Earth and doing scientific information.
Exactly. So if you imagine, I mean, we think of satellites that are using maybe 100 watts or so, which is sort of the order of several light bulbs of energy, really. And at that level, it means that you're talking about using lasers. So a laser that is delivering, say, 500, 600 watts of power, which is quite a lot in laser terms, but quite achievable actually. Would give you enough energy, and once you account for things like conversion efficiencies, to actually produce that level of power and more. Those, I think that's one of the things, that because the power levels that we're talking about here are relatively small compared to some of the really big projects like space-based solar power, which is on orders of magnitude above that. So this is at a level where it becomes a bit more achievable when you think about what is sort of normal laser technology that's available, and the type of things you're driving on the satellite or you need to do. So it brings it into what I would say is an achievable range.
And so, I mean, I'm assuming this is space-based. Is there, if you're going to be going thousands of kilometers, you're going to want to keep your power satellite in sunlight as long as possible. Are there some orbits that you're looking at to be able to do that?
Yeah, so I mean, actually, I'm not the specialist in the satellite dynamics, but yes, I think there are 2 approaches here. One is that you actually can have a satellite in low Earth orbit that's just a bigger satellite that has bigger solar panels and does have the big battery, let's say, that can still provide, even when it's eclipsed, it can still provide the other satellites. Or you put the satellite that's in a higher orbit where it has a longer exposure to the sun, right? And then, of course, you increase the transmission distance that you would need. So I think, for example, Space Power are looking at different ways of achieving this in terms of the orbits that they would use. But as I say, it can be literally that you just do most things in low Earth orbit, and you just instead of having you might have a few master satellites, if you like, that are the power stations or power providers for your grid that you're creating.
Assuming your aim was good, how efficient is this process? Like, how small of a solar panel could you get to power your satellite, even if you're transmitting this power over thousands of kilometers?
Yeah, so you can actually one thing you would actually do is at the laser end, you would initially expand the beam, so that and the reason you would do that is so that when the beam then transmits, it doesn't diverge very much. And so if you think about a laser pointer or something sort of very familiar, they're very narrow beams, and they diverge. You'll see quite a lot of divergence over distance. But if you make the beam bigger to start with, then that divergence is smaller. So you can, look at then having beams that are, maybe sort of the order of tens of centimeters or something across, that then transmit onto a solar panel that's of similar dimensions, if you like.
Oh,
And that
interesting.
again, that becomes
Sorry. So just to understand this. So in other words, that if you diverge the beam on purpose to a larger size, then it will remain coherent for a longer
yeah.
distance.
So what you're doing is you're sort of not divergent as such. You're increasing the width of the beam.
Hmm.
So if you like, you start off with a wider beam, and then the divergence of that beam actually is lower over distance, because so it's one of those things that if you're starting off with something very, very, very small, you'll see a big effect on its divergence. Whereas if you make it bigger, you will see a smaller effect. So that's quite a standard thing to do, actually, to maintain a sort of more collimated beam.
Now, this is sort of thinking about this from space. Is there any way to do this from Earth?
Yeah, I mean, and actually, people have thought about this as well, about doing similar types of power beaming from Earth. Now, the sort of the pros and cons of that are, doing something from Earth on one hand is a lot easier, because you don't have to launch it.
Yeah, it's right there.
Launch your
Yeah.
transmitter. But the other thing you have to put up with is the atmosphere, and that's where you then have to be very selective in terms of what you're doing, because as you know, the atmosphere has a very strong effect on light. So we know that from just looking at the sky, and looking at the blue sky, and looking at red sky in the evening, and so on. So there's a lot of scattering and so on that we have in the atmosphere, and that's very wavelength dependent. And so if you were going to do it from the Earth, you would have to pick what we call atmospheric windows, so wavelengths of light that would find their way most easily through the atmosphere. Now, you can find those. Actually, there are some wavelengths that are where the atmosphere is actually very transmissive. Actually, you can get well over sort of 95% transmission at certain key wavelengths, in the infrared, for example. But they also change depending on the conditions. So if it's cloudy or lots of water vapor, then you might even then still see more scattering. So it is possible, and indeed, as I say, people have considered this, but you just have to think more because of the atmosphere and the atmospheric effects.
But it is interesting. It's sort of like the opposite of everyone thinks, oh, we're going to send giant satellites to space and they're going to use, say, microwaves to beam the power down to Earth. But actually, the sort of simpler application that can help develop the technologies to go the other way, to provide the power to the satellites from Earth and learn from there.
Absolutely, and there have been lots of experiments of using lasers through the atmosphere for various applications. Actually, not just power. I mean, and there are some other applications. For example, there's some really fantastic work going on to try and use lasers for LiDAR, for looking at positioning, spatial awareness, and looking at where satellites are and tracking them using reflected laser light. And again, you always have to think about the atmospheric conditions when you're doing that. So there's a lot of opportunity as well for doing applications that are pointing the laser upwards.
And so, like, what about the loss of efficiency? So, like, say you've got your big space power satellite. It's receiving all of the light from the sun, whatever's the efficiency of the solar voltaics on the satellite. It's then converting that into a laser, firing it to the secondary satellite. The secondary satellite is using a voltaic system to turn that into energy. What kind of loss do you think you're getting across this chain?
Yeah, that's a really good question. And I mean, I guess the basic answer to that is it varies, and that's obviously one of the parameters that we're quite interested in improving. But if you look at a solar panel on board a satellite, it maybe it's working at 30 to 40% conversion efficiency of the sunlight into electrical energy. And then you're powering a laser, and a laser may at the top end, you might get it sort of like 50, 60, 70% you can get as an efficiency in a high power laser, actually under the right conditions. But reasonable sort of numbers, you might say, well, let's say 40 to 50%. And then at the other end, when you get to the receiver on the satellite, you're again looking more like 40 or 50%. conversion efficiency there, and of course those all multiply through.
Yes.
And so you then end up with an efficiency, and it might be, for example, it could quite possibly be 20% or even lower. Now, actually, for a lot of applications, that's not such a problem. The fact that you can do it and deliver the energy when you need it, the efficiency is less critical, if you like, because it's energy that's there and you're just getting it from the sun all the time anyway on your master satellite. But of course, there are ways that we can improve that. And so the sort of things that we work on are, again, for example, well, what can we do? At the very beginning, you say, well, what can we do about the photovoltaics on satellites to make them more efficient? And there's a huge amount of research going on in things like multi-junction solar cells and so on that very effectively capture as much of the solar spectrum as possible. And then you've got research on lasers. And I say the lasers can get very high efficiency. So the conversion efficiency of high power lasers can be extremely high. So then at the other end, like I say, when you're collecting that laser light on the photovoltaic on your smaller satellite, then again, that efficiency of conversion is very sensitive to wavelength. And so what we've spent quite a bit of time looking at in the research is, well, what wavelengths are best? What wavelength could we use? And actually, we've looked at several. And for example, maybe even you could use more than one wavelength, right? And so for some satellites and for some types of solar panel, that's what you want to do. You actually want to use several wavelengths to actually then optimize the efficiency of the system. And then for the other factor, of course, that comes into that is what is the operating environment of that satellite? And so one thing that's very interesting about satellites in eclipse is that the temperature, if you like, is quite low. And one very interesting thing about photovoltaics is that when the temperature drops, their efficiency goes up. And so in our lab tests, for example,
that's ironic.
It's just some really, really nice physics that when you cool down the semiconductor that's forming the photovoltaic, you tend to get rid of the what we call the loss processes, the things that essentially produce heat rather than anything useful. And so you cool it down and you can start to reduce those. And so in our lab trials, for example, we've had solar cells that we were getting efficiency of about 30 or so percent, let's say, under normal room temperature conditions. And when we cool it down to cryogenic conditions, you're getting over 70%. So you can get quite a big increase.
That's really
in
interesting.
Conversion efficiency.
I had no idea.
So
I guess no one had found out. Like no one had tried gathering sunlight in the dark.
Yeah, and it's very interesting again because I remember having conversations about this with people a few years ago and said, we've done various experiments in the lab in cryostat systems. So this is taking it down to sort of liquid nitrogen type temperature, so sort of below 100 Kelvin. So these are pretty cold conditions, but not unreasonable conditions for that kind of environment. And so when I spoke to people that work in the space sector, and I was saying, well, actually, there are situations where this could be useful, and it's not just the sort of things we're talking about just now, but even things like lunar exploration in polar regions, that kind of thing, where it's dark and it's cold, and in those cold conditions, your photovoltaics are very good.
Well, and that sort of leads into the next sort of series of questions that I wanted to talk to you about. Is it feels to me like this is ideal for, say, being able to have rovers in the permanently shadowed craters on the moon. Have you sort of been suggesting this technology to NASA and others looking to send rovers into those regions?
Yeah, this is something that's being discussed actually in various areas and by various players working in the sector. It is potentially very interesting because, of course, if you're thinking about some lunar rover doing exploring a crater or something, I think one of the risks of that is always if you have to bring it somewhere to charge it. If you have to always take it back somewhere, then there's always a risk whenever you have to do that. If you want to tether it with something, that's also a risk. But if you could just have something where it's just effectively got its own sun that's providing energy to it, either from maybe again it could be a lunar satellite that you're using to power the rover, or it could just be a big something on a big pylon or something, a big post where it's just delivering energy down into a crater from a laser. So I think it could be very interesting to see how that might be applied.
Does the do you think that the laser that you need, like, will the efficiency need to change over time? Like, as the distance changes, as the temperature changes, would you change the nature of the laser to match the conditions? I don't know if I'm making
Yeah, I
sense.
mean, yeah, no, it's a good question. I mean, the for example, it depends on the environment and what's in that environment. So, for example, uh, one of the sort of good things about using these lasers in the low Earth orbit satellite environment is there aren't any people there, right? So you don't need to worry so much about some of the normal things that we consider with lasers and safety and so on, in the sense of anything that gets in the way of the beam. If you're using it in environments where there are other factors involved, or there might be potential exposure to people and so on, then you choose wavelengths that we consider to be eye safe. And so again, that applies also a lot to obviously things on the terrestrial applications. But we've again done quite a lot of research on how you make what we call eye safe systems, and those are operating at wavelengths that we know are actually safe in terms of the way that they interact with the human eye and the human skin and so on. So again, there are other factors like that that are important. And if we're doing it in an environment where there is an atmosphere, then of course, as I mentioned earlier, we have to think about factors to do with laser transmission and what might cause attenuation of the beam or scattering of the beam in other ways. So for example, if we're looking at things like planetary exploration, and using rovers on other planets and doing similar things, then yeah, we'd need to think about that, and we'd have to be selective about what we use.
Now, one of the big issues with, say, these mega constellations of satellites like Starlink is the impact that they're having on astronomy. They are relatively bright. I mean, you can't see them with the unaided eye, but they are definitely a problem for big telescopes. And a big chunk of this is the reflection that is coming off of the giant solar panel. So, do you think that if you went this route, you could decrease the visibility of a satellite?
Yeah, I suppose that's an interesting point as well. I mean, in some senses, I would say yes, because you could reduce the size of the panels that you need on some of these small satellites. So you reduce the reflecting surface area, if you like. So yes, in that sense, I would say that's possible. And even I suppose if you took it to its extreme and said, well, could you make something that basically just relied on the laser and didn't actually even need to have the solar illumination at all? Then you could engineer the panels, maybe they don't even reflect in the visible part of the spectrum, so that you actually don't see some of that reflected light. So I mean, that's this kind of like thinking about possibilities really. But yeah, I think the fact that you can physically reduce the size is an important factor. And also, one of the nice things about photonics again is that we can structure surfaces to control the way that light is reflected off the surface. And of course, if you're in the business of making solar panels, light reflecting off the surface is waste, right? Because if a good solar panel absorbs all of the light hitting it, and again, so I think there's a good piece of engineering challenge there to actually improve that. So yeah, I think there is opportunity.
All right.
To
Well,
improve
we'll pass that feedback along to Elon Musk then. But then I guess on the flip side, you've got lasers zapping around in space. Would that hinder astronomy in any way?
Well, I think the good thing about, in some senses, I would say that the good thing is that we are using very specific wavelengths, and they're very narrow, right? So the other thing about a laser, of course, that's different from other light sources. So if you think about even like a light bulb or the sun, they're very broad. So spectrally, the number of wavelengths there is huge. They're very broad spectrum. Lasers are extremely narrow, so they're very well defined wavelengths, and so that means that we can, for example, if you know that there's a wavelength there that may be a problem, if you're doing some observational astronomy or something, then you could look at filtering that wavelength. And if that wavelength is away from the sort of light that you're interested in, then that actually poses less of a problem as well. So again, I think the good thing about having control over that wavelength is it means you can take that kind of those sort of things into account in the design.
And so, as long as you don't point it at people's telescopes, it should be fine because it's going from point to point.
Absolutely. And Actually, interestingly enough, I mean, some of that, depending on the telescope, type of telescope, but it could actually even be blind at the wavelength that we're using, right? So if you're doing visible, if you're focusing on visible astronomy, visible light astronomy, then some of the wavelengths we use, you wouldn't even detect it. It wouldn't even register.
Yeah.
So again, but of course, astronomy covers many wavelengths, covers a very broad spectral range. So you'd have to consider that.
Yeah, I mean, I can imagine like maybe if there's a heat signature from in the infrared, so it might not be visible light, but maybe it casts a bigger infrared signature because the heat is concentrated into a smaller area as it's being gathered. I'm not sure, but it's just an idea.
Yeah, but I guess one thing I would say there is that, again, because the laser light has such a narrow spectral range, it means that you can create filters, like optical filters on your telescope, that just knock that out.
Yeah.
Right. So that you don't see it, doesn't get to your detector.
So you could sort of talk with the astronomical community and say, okay, we're going to be giving off this wavelength of light, which is, not that useful to you or whatever. Let's agree that this is what kind of wavelength we're giving off so that you can deal with it appropriately.
Absolutely. Yeah, and even before that, at the design stage, is say, right, we actually have a choice here of wavelengths that we might use. Which from your perspective, which of those is going to be actually present the least problem, really, or won't present a problem.
So this is super cool. I'm really excited. I think it's a great use for this technology, and I can imagine the work having lots of other applications, but I want to now shift into the speculative portion of this interview. So I understand, there might be people who are wary about you making things. So this is all we're just hanging out in a pub, speculating about the future. So let's talk about this technology. I mean, obviously, we're all tethered to all these stupid cords all the time in our lives, and people have been promising wireless power distribution for quite a while, and yet it never seems to appear. Do you think that some kind of wireless power or wireless recharging is feasible?
Yes. Of course, we do already have some forms of wireless charging, right? So most modern smartphones will use wireless charging. They'll do some sort of inductive charging, for example. Now, of course, that's close proximity. You put your smartphone down on effectively on a charging pad.
Yes. But there's no lasers. There are no lasers coming out of my little charging pad.
No, that's right. So now, but actually, in terms of doing wireless charging using lasers, this is already demonstrated actually, and it's another thing we also work on. And again, as I was saying earlier, the one main thing we think about when we start to look at, let's say, consumer applications of charging. So let's say, I want to charge my phone or my iPad or whatever it is wirelessly. Then we can do that. We can already do that. If we have a laser system, for example, in an enclosure in the ceiling of a room, you might have your light or something like that, then that could be essentially beaming energy down to any device that you want to operate. It could be using some image tracking to know where the devices are in a room. And the key thing there is that we need to have that operating in what we call an eye-safe mode. And again, that comes down to the choice of wavelengths. And we've already worked on the particular wavelengths in the infrared that we know are eye-safe. And so with those types of systems, we can do wireless charging. Of course, what you need at the other end is the photovoltaics. So you have to have something built into the receiver that is going to then do the conversion for you.
But I'm assuming
technically it's feasible.
The range is fairly small. I mean, you're only a few meters away from the laser.
Yeah, that's right. Yeah. So, and again, in fact, there's a one or two companies already that are looking at sort of commercial demonstrators of this kind of system for an office or a home environment. And it's doable. I mean, the technology is already there to make this happen. And so really it's a case of I think the sort of things that come into, I guess, question there will be what efficiency can you do that at? And if my thoughts on that are that you may be a bit more sensitive to efficiencies when it's in more of a regular application. And that's where sometimes you have to think about what the conversion efficiency will be of that system compared to something like induction. So I think that's one thing. And there are other areas perhaps where, for example, we know that we're already in a revolution in terms of vehicles, right? Electric vehicles. And we're now looking at essentially moving completely away from for internal combustion engines over to electric vehicle technology. And certainly there's a lot of pressure and push to do that over the next decade or two. But you need to be able to charge these vehicles, right? And so again, you need, ideally, what you want is some wireless way of charging. And it could be, let's say, in the future that we come up again with systems that are based on either laser, or it could be a microwave or other method that we will use for doing wireless charging. So I think, sort of coming back to your question, really, my perspective on this is that technically it's becoming much more feasible to make wireless charging a reality, and there are more applications now that demand it. And so I think we will see this increasing over the coming decade.
And it's an interesting balance, right? When I think about my phone, the weight of my phone is mostly its battery. And the battery is there to last me one whole day. And the amount of energy that it uses that I have to recharge that phone is negligible. I mean, it's whatever, a couple of dollars a year, a month, whatever it is to charge that phone. And so if I could be sitting around inside the house or in the office or whatever, and there was a laser just keeping that its smaller battery topped up, then I would have a much lighter phone that would kind of never seem to run out of energy unless I'm away from inside, if I'm outside, the terrifying place we call outside. And I guess the same thing with electric cars. Like, imagine if you had an electric car that had a 20-kilometer range battery in it, and then was receiving, as it was driving along the road, was receiving general top-ups from the road itself, and so on. And it's only if you want to go further afield do you need a different kind of vehicle. It's kind of a fascinating idea.
I think it's interesting because, of course, there's a lot of research going on at the moment into battery technologies. I mean, that's one of the biggest areas of research, really, in sort of, I guess, materials and so on research. But of course, yes, we could get bigger and bigger batteries for things like electric vehicles, and they are now allowing like really quite large ranges. But you're right. I mean, we could actually say, well, maybe we don't need to carry all this mass around in the car.
Yeah.
We can just regularly charge it, and therefore also, again, it's a very similar argument, isn't it, to the one we just discussed for the low Earth orbit in a way.
Well, that's exactly
you just reduce the materials costs.
Yeah. I mean, the analogy is that we plug devices in. This computer that I'm using is plugged in. So imagine if I had to run it off battery power and then recharge it every now and then. It would be a completely different machine. My whole life would be utterly different if there was no such thing as wires to continuously power the devices that I use. And yet we are shifting to a certain portion of our lives running on these battery, the things that need to move are battery operated. But what if they didn't need to be battery operated? What if you could have them, maintain continuous power wherever you went? It's kind of fascinating, because then it makes them cheaper, simpler. You have one laser mast that you set up in your yard, and then suddenly devices are getting power nonstop.
Absolutely. And I think to be honest, probably one of the other factors involved in that is, as I said, if you look at the future of energy and say, well, look, we are going to have to reduce our reliance on fossil fuels and so on, and the world is getting a bit better at that, and there are actually quite sizable installations for things like solar and so on. But we will have to do that, and of course, if we can go completely renewable at some level, let's imagine we can get all of our energy directly from the sun in a direct way, in renewable forms. Actually, then perhaps some of these wireless charging approaches where the efficiency might not be the greatest. It's less critical if your energy source is a renewable source. I think sort of from an environmental perspective. So that probably also opens up more applications that become acceptable applications in terms of how we deliver energy to things.
So let's talk about the exploration of, say, the outer solar system. Once you reach Jupiter, the size of your solar panels is like 25 times as big as what you would need here on Earth, and the efficiency just dropped from there. The solution is you put in, say, a nuclear RTG, something that's like a nuclear battery onto your spacecraft, but that doesn't solve the problems for smaller spacecraft. So can you see this providing solutions where, I mean, I'm sort of envisioning, right? Like if you're going to have, like, say on Mars right now, we have Perseverance and we have Ingenuity. We have this tiny little helicopter, and the helicopter has a solar panel on top with a battery, and it's flying around. But imagine you tried to do a similar thing, but on, I don't know, the moons of Uranus, to have some sort of smaller devices that are working. This seems like another really great application where you take a fusion reactor or fission reactor, and then it is beaming power to various smaller devices, people's phones, whatever, to be able to keep them supplied with power.
Yeah, absolutely. I think again, it's sort of like just providing a link in the chain, isn't it?
Yeah.
And it can fit in with other forms of energy and how that's being delivered. So absolutely. I think it's about versatility then, isn't it?
Yeah, it feels like you're almost like redefining what wires are. That there's a laser wire. There's a kind of wire that you can have that in some cases it's the right application. In some cases an actual wire makes the most sense, but for other applications, and then if you can balance this between wires, power generation, batteries, and mix and match all of these different tools to give you the best sort of economy depending on the need.
Yeah, and of course you're mixing up sort of the conduits for energy and data, right? So again,
that's really interesting.
With using light, you can, well, as we were discussing earlier, I mean, light, we use light for communications all the time, and we can do that. We can couple it onto the same channel, so we can have our laser beam sending our energy, but we can also put a small modulation on top of it, and then it's sending your data as well. So you can use that one system for providing your power and data link.
So you, instead of having Wi-Fi, you would have a laser, which is like it hitting your phone at fiber optic speeds, that is providing power and providing your uplink to the internet.
Yeah, why not? I mean,
Wow,
you obviously need to think about the bidirectionality aspect of it, but in a way that, I mean, there are other technologies being developed now. In fact, they're getting very well developed in things like Li-Fi. So this sort of light-based form of communications. So again, doing that approach by having the laser power terminal, if you like, could give you high speed connection, certainly high speed download from the internet directly to your device, plus the energy to run the device.
That's really interesting. Now I dismissed the idea of beaming power from space, but I think, for a lot of people, that's a very exciting idea, and it's considered one of the justifications for creating a civilization in space, for us to build giant space satellites that are beaming power to Earth. Do you think that that's in any way feasible? Or because the comparison I always make is like, there's so much power falling on the Earth from the sun, and it's so much cheaper to just set up a solar panel than to try and fly a satellite to space to then send that power to Earth. Do you think there's any feasible application for beaming power from space down to Earth?
I think it's I think one of the issues with, I mean, I think you make a good point there, right? So I think one of the issues about let's just have solar panels on the ground idea is that depends a huge amount on your geography, where you are on the planet, in terms of how much energy you're actually going to get from that. If you're living in equatorial regions or something, then you've got a pretty well defined and nice steady stream of sunlight. If you're living in northern climates, I mean, if you're living in Britain, actually where I am now, then you've got cloud cover quite a lot.
Yeah, we have the same here in Canada.
So you can't rely on this. So I think there again, it's one of those things where I think what we need to have is a very diverse approach to this. And so space solar power, I think, tries to overcome some of those issues where actually you can deliver energy where you need it, and it's essentially becomes independent of where that is. and there are big projects on this. So there's a big initiative in this country, in the UK, the Space Energy Initiative, to try and look at doing this. And I mean, that's mainly based on a microwave approach, but of course the laser approach is another method being considered. But even within that, of course, the other thing to think about is, if you're going to start building these very large structures for a space-based power station or a space station or whatever you're making, you need to build it. And so the other application for wireless power in space potentially is, well, powering the robots that are going to do all the work, right? So all of the machinery that you're going to need to actually do this needs energy, and sometimes that's going to be quite hard to access and so on. And again, you might want that those robots are agile and not carrying massive batteries and so on. So we'll deliver the energy to them. So I think that's the way I view it. I view that there are some big picture things that you can think about in terms of, like, let's build a big power station in space. And I actually, personally, I think that may be something that does actually happen. But there are steps that require to do that will need energy. And so some of the approaches that we're talking about now, I think, can help fulfill that need.
But like, when you think about, say, the cost of per kilowatt hour for solar panels, I mean, it's just dropping precipitously at this point. It's just a couple of dollars at this point. It's still on this technological growth curve.
Absolutely.
Decreasing in cost every couple of years, nearing zero. And yet,
I think there are some very significant advances in solar cell technology, and things like the perovskite materials are very up and coming, have had an enormous growth in the last few years, and I think will also be there to fulfill an important demand. But equally, there are other materials. There's some fantastic work going on materials that are, it seems like a bit of a contradiction, but transparent materials that you put on your windows that are solar panels. But they actually capture energy reasonably well, and allow enough in for you to actually use it for lighting and so on. So there are lots and lots of different things going on to develop solar materials. So as I said, I think it's not one solution. It's a series of different solutions to make solar panels. Some of them will be in your home, and maybe some of them will be somewhere else, but are delivering energy to your home. I mean, indeed, if going back to the thing about the cloud cover and so on in the northern parts of Europe, well, maybe if you were delivering power to those panels using lasers, that would be a supplement as well. But I think that's another interesting area that needs further exploration.
So now we're going to get even more speculative. So buckle up. So one of the ideas, space junk is becoming a bigger and bigger problem, and there's been lots of ideas to start to clean up some of the space junk. But the most feasible idea, the idea that I like the best, is using lasers. That you fire a laser at a piece of debris, ablate a little bit of its material to slow down its orbit and hopefully help it reorbit the Earth's atmosphere and try and clean up a lot of that space junk. Do you think that, what kind of power of a laser is required for that kind of activity compared to, say, communication or power beaming?
Yeah, so I think if it's talking about ablating, if you're literally talking about using it to sort of essentially degrade the material, then you're talking a lot of power. I mean, typically, you're using multi-kilowatt power lasers to do, if you wanted to do welding or something on Earth, then you might be looking at sort of like 10 kilowatt laser or something like that. So you're looking at high power, significantly higher powers, and it's not just the power, it's the concentration, because the intensity, if you like, because when I was talking earlier about how we would deliver a laser beam over a long distance to a satellite, where I would say, well, we would broaden the beam, we'd make it wider so that we get better transmission. If you're wanting to use a laser to over a long distance to hit an object that you want to cause some sort of physical damage to, or some sort of physical degradation, the intensity's got to be high enough. And so that's a challenge, I think, to deliver, because then you need to have you really have to look at very high powers to achieve that. So I think that kind of approach, or that application is in principle possible, I think, but I can see lots of challenges. in how you make it work in practice, especially if it's looking over quite large distances with very high intensities.
Yeah, you can imagine people being a little nervous about nations launching lasers capable of zapping and just, even just ablating material off of pieces of space junk from hundreds of kilometers away. Like what if you pointed at their satellite? What if you pointed at
Yeah,
their optics? What if you pointed at the ground? So I can certainly understand that there are concerns, but we, space junk is a big problem, and at this point, how do you clean up 100,000 pieces of garbage? There
absolutely.
isn't another solution that I think is feasible.
But as I think I mentioned earlier, one of course where lasers can be helpful there is using lidar techniques to know where all those pieces are, so that you can very well track them, even smaller, relatively small pieces of debris that you can track using sort of lidar imaging techniques. But of course, that's sort of helping understand the problem and where the problem is, but it's not solving the problem. So that other approaches I think there are important. But again, one of the ways that you stop that becoming a big problem is you don't launch as many things, and you don't have to launch as many things if you can make them last longer by, again, having maybe the energy source that they need that keeps them more operational.
That horse is already out of the barn. I mean, we are already in the tens of thousands of pieces of debris in low Earth orbit, some of which are in orbits that are going to take thousands of years to degrade. So, at some point, there will need to be a solution to solve this, and you can't just go and catch them all and bring them back. I mean, for sure, you can try to be better about thinking about the future and make sure that you have a plan for the end of life of your spacecraft. But there's already a lot of debris up there, and as we add more satellites, there's the potential that they're going to collide into, smash into each other and create more debris and on and on. So, we may get to a point where this is the only technology. I mean, I can totally see that there are many worrying downsides, but I wonder about the sort of the feasibility. Now, are you familiar with the Breakthrough Starshot Foundation?
A little bit, but not very.
Yeah, well, the idea is, I mean, it's the idea of laser sailing, that you are,
yes,
you take a solar sail and you fire a laser at the sail and accelerate it to significant, speeds. Have you thought at all about what kinds of lasers might be best for doing laser sailing?
We haven't. It's not something we've looked at.
Yeah.
But yeah, I was aware of that, and I did look at it with interest. I mean, there are things to consider there in terms of what it is you're essentially targeting, and again, it's always the same thing. You always look at, well, what's the optimum wavelength to do that? What's the optimum way of delivering the energy, for example, in a pulsed form, to supply that energy in an effective way? So, yeah, I think that's a whole area of interest. It's not something we've worked on, but certainly it's something I'd be interested to watch further.
I mean, I think about it like you've got the laser, you've got the amount of power that you're trying to provide, but you don't want to melt your spacecraft when it's relatively close to the laser, but then it's going to be accelerating away from you at a pretty high speed, and maybe you're continuously zapping it for some period of time, and so there's going to be a bunch of factors that you're going to have to change over time as your spacecraft is moving away. For the smaller versions, maybe you're accelerating it for just a few, maybe, I don't know, a few 100,000 kilometers. But I've heard ideas on even bigger versions that you might accelerate from the Earth out to, say, the orbit of Pluto before you can no longer, hit it with your laser and it's off, and it's already now going 20% the speed of light. So it'll be interesting to think about all the dynamics of that whole system as you go.
Yeah, absolutely, and also where the laser is, right? I mean, where do you position that laser, and is there an optimum position to put it that's in orbit or somewhere, somewhere off the surface of the Earth, obviously. So,
the far side of the sun, just to be safe. Right.
Yes.
Just so nobody is concerned about what this laser is capable of, because it would be
absolutely.
a very powerful laser. And so if we were looking in the sky for advanced civilizations that were using very powerful lasers for communication, for power beaming, for laser sailing. What could we look for?
Yeah, that's an interesting point. I think, well, first of all, it's I guess one thing you have to think about in terms of probabilities, because of course to be able to see it, you either have to be in line of sight, or it has to be that laser light has scattered off something that brings it to you, right? So, it's sort of like sort of classic sort of movie images of lasers where you see these like red lines shooting around. Of course, you don't see lasers unless you don't see the beam until you actually disturb it in some way. So as I say, it depends on if you're within the sort of line of sight of the beam or if it's scattered towards you somehow. The second thing, of course, is you need to be able to detect it, and you probably need to detect extremely small light levels. Now, there's been huge advances in things called single photon detectors, actually, and so these single photon detectors are getting very good at detecting extremely small numbers of photons. And I imagine, that this is what we would have to be looking for. And if this was coming from some, intelligent being somewhere else in the universe, and it was within a sort of a achievable distance of us, let's say, then you would look for patterns in that.
Right.
You would look at on your single photon detector, you'd look at patterns in the signature that's coming through that don't look random, that look as though it may have something behind it. So I guess that's what you do.
Yeah, yeah. What about using photons as a form of propulsion, like a photonic drive?
Yeah. I mean, in terms of, it's interesting, of course, because photons have hardly any momentum. We most of the time we assume that we call it zero. We think of photons as just having zero momentum. Yeah, I think it's an interesting area. I mean, again, I don't know. It's not an area I work in, in terms of people trying to do that. But I can see that being quite challenging.
I mean, do you think about it in the over time as you are using lasers on your spacecraft, it's going to be receiving a kick in the opposite direction that you may have to eventually compensate for?
Yeah, that's an interesting point. My sort of gut reaction to that is that it will be so tiny compared to everything else that you're doing that you might not even barely register it.
Yeah.
But when you're starting to look at extremely long journeys on spacecraft at some point in the future, then maybe there are some little corrections that need to be made. But it's an interesting point.
Yeah, very interesting. Well, Stephen, it's been absolutely fascinating. Thank you for answering every single question that I had about lasers and space power. It was a pleasure to dig as deep as down into this rabbit hole as I was wanting to go. I appreciate you humoring me. Thank you.
Thanks very much. It was a pleasure.
If people want to follow your work and keep track of the project, especially the work you're doing with the space power, what's the best way to do that?
Well, if you just Google, use the mighty Google to look at the University of Surrey and my name and Space Power, the company. So Space Power have got a nice website that you can look at and see what they're doing and how things are progressing for them. So that I would suggest doing that, and then watch out for what comes on the news.
Well, fantastic. It sounds really exciting and has the potential, I think, to fundamentally change the way we transmit power both on Earth and in space. So I'm really looking forward to whatever this turns into.
Absolutely.
All right. Take care.
Excellent. Thanks very much.
Bye-bye.
Bye.